You know, science has spent the last few hundred years doing something rather fascinating. We keep looking deeper into the structure of the world. First, we looked outward and discovered planets, stars, entire galaxies. Then we started looking inward into matter itself. A droplet of water on a leaf looks smooth to the eye. But zoom in and you find molecules. Zoom in further and those molecules become atoms. Go deeper and you find electrons, proton, neutron, and even smaller particles hiding inside. Every time we build a better instrument, nature seems to reveal another layer. It's almost as if the universe keeps unfolding the closer we look. But that raises a very interesting question. Does this process continue forever? If we had a perfect microscope, could we keep probing smaller and smaller distances without end? Or is there a fundamental limit, a smallest possible scale of space itself, where the very idea of distance begins to break down? Let's start with something very simple. 2 electrons. An electron is one of the fundamental particles of nature. It carries a negative electric charge and it also has mass. Now imagine placing 2 electrons some distance apart from each other. Call that distance r. The moment you do this, 2 different forces appear between them. One of them is gravity, because anything that has mass attracts anything else that has mass. The other force is the electric force, because the 2 electrons carry the same electric charge, and like charges repel each other. So these 2 electrons are in an interesting situation. Gravity is trying to pull them together, while the electric force is trying to push them apart. The question is, which one wins? To answer that, we can simply calculate the strength of each force using the basic laws of physics. The gravitational force between 2 objects is given by Newton's universal law of gravitation. It says that the force is proportional to the product of the masses and inversely proportional to the square of the distance between them. If both particles are electrons, then each mass is just the mass of the electron m. So the gravitational force becomes g multiplied by m squared divided by r squared. Now let's look at the electric force. For charged particles, we use Coulomb's law. This law looks surprisingly similar to the gravitational one. The electric force is proportional to the product of the charges and inversely proportional to the square of the distance between them. Since both particles are electrons, both charges are just the electron charge E. So the electric force becomes E squared divided by 4 pi epsilon naught times r squared. At this point, something very interesting happens. If we want to compare the 2 forces, we can take the ratio of the electric force to the gravitational force. When we divide the 2 expressions, the r squared in the denominator cancels out. That means something quite remarkable. The ratio between the electric force and the gravitational force does not depend on the distance between the electrons at all. Whether the electrons are a meter apart, a centimeter apart, or separated by atomic distances, the ratio remains exactly the same. So now all we have to do is plug in the numbers. We substitute the charge of the electron, the mass of the electron, the permittivity of free space, and Newton's gravitational constant. When you go through the calculation, you get an astonishing result. The electric force between 2 electrons is roughly 10 to the power of 42 times stronger than the gravitational force. That number is almost absurdly large. It is a 1 followed by 42 zeros. If you actually write it out, it fills an entire line of text. What this means is that gravity is unimaginably weak compared with the electric force when we are dealing with individual particles like electrons. And yet, strangely enough, gravity is the force we notice most clearly in everyday life. It is gravity that keeps us on the ground. It is gravity that holds the moon in orbit around the Earth and the Earth in orbit around the sun. So how can the weakest force in this comparison dominate the behavior of the universe on large scales? The answer lies in a simple but subtle fact about matter. Most objects around us are electrically neutral. Inside every atom there are positively charged protons and negatively charged electrons. Their charges cancel almost perfectly. As a result, when you look at a large object from the outside, you do not see the enormous electric forces that are happening inside it because they balance out. Gravity is different. As far as we know, there is no such thing as negative mass that could cancel the gravitational pull of positive mass. Every piece of matter contributes to gravity in the same direction. So even though the gravitational force between individual particles is extremely weak, the effects add up. When enough matter gathers together, gravity becomes the dominant force shaping the large-scale structure of the universe. It is gravity that pulls enormous clouds of gas together in space. Those clouds collapse to form stars. Inside star, nuclear reactions create the chemical elements. When stars explode, those elements spread through space and eventually form new stars, planets, and in at least one known case, life. So in a curious way, this incredibly weak force ends up playing a fundamental role in the story of the universe. But our little calculation also suggests something else. According to the equations we just used, the ratio between the electric and gravitational forces should stay constant no matter how close the electrons get to each other. That seems straightforward enough. However, nature has a way of surprising us when we start pushing things to extreme limits. And it turns out that once we begin squeezing particles into very tiny regions of space, the simple picture we have just described begins to break down. At first, this result feels almost absurd. If the electric force between two electrons is 42 orders of magnitude stronger than gravity, you might reasonably expect the universe to be dominated by electricity rather than gravity. In fact, if the electric forces inside ordinary matter were not balanced almost perfectly, the world around us would behave in a completely different way. Objects would not sit quietly on the ground. Even the tiniest imbalance of charge would produce enormous forces capable of throwing matter apart. But nature has arranged things in a very particular way. Most matter in the universe is electrically neutral. Inside every atom there are positively charged protons in the nucleus and negatively charged electrons orbiting around it. The charges are equal in magnitude but opposite in sign. So when you look at an atom from the outside, the electric fields cancel almost perfectly. The enormous electric forces are still there inside the atom, holding the electrons and nucleus together. But they are hidden from the outside world because the positive and negative charges balance each other so precisely. This is why you normally do not notice electric forces between everyday objects. A table does not suddenly repel a chair across the room because the charges inside them are balanced to an extraordinary degree of precision. If even one extra electron were left unbalanced among a trillion atoms, the resulting electric force would be easily measurable. But because matter is neutral overall, these powerful forces effectively disappear when you move beyond the atomic scale. Gravity behaves very differently. Unlike electric charge, mass only comes in one sign. At least as far as we currently know, there is no such thing as negative mass that cancels positive mass the way negative charge cancels positive charge. Every piece of matter contributes to gravity in exactly the same direction, always attracting everything else that has mass. The gravitational pull from each atom may be incredibly small, but the important point is that all of those tiny contributions add together. Imagine taking a single atom. The gravitational attraction it produces is essentially negligible. Now imagine collecting not one atom, but trillions upon trillions of them into a large cloud of gas floating in space. Each particle attracts every other particle, and although each individual pull is tiny, together they begin to matter over vast distances and enormous numbers of particles. Gravity slowly wins. This is precisely how stars are born. In the cold regions of interstellar space, there exist enormous clouds of gas and dust. These clouds are mostly hydrogen, spread out across distances larger than entire solar systems. At first, the particles drift slowly, but the mutual gravitational attraction between them causes small clumps to form. Those clumps attract more matter, which increases their mass, which in turn strengthens the gravitational pull even further. Gradually the cloud begins to collapse inward. As the collapse continues, the gas becomes hotter and denser. Eventually, the conditions at the center become extreme enough for nuclear fusion to ignite. Hydrogen atoms begin to fuse into helium, releasing enormous amounts of energy. At that moment, a new star is born. What began as an incredibly weak gravitational pull between countless atoms has now created a blazing star capable of shining for billions of years. Gravity continues shaping the universe even after stars form. Massive stars eventually run out of fuel and explode as supernovae, scattering heavy elements into space. Those elements later become part of new generations of stars and planets. The calcium in your bones, the iron in your blood, and the oxygen you breathe were all forged in the cores of ancient stars that existed long before the Earth formed. And the reason those stars existed in the first place is because gravity slowly gathered matter together across enormous distances. So despite its incredible weakness on the scale of individual particles, gravity dominates the architecture of the cosmos because it never cancels out. Electric forces can be extremely strong, but they hide behind the neutrality of matter, gravity. On the other hand, always adds. It accumulates across astronomical amounts of mass and time, eventually sculpting galaxies, star systems, and planets. This contrast between the enormous strength of electricity and the quiet persistence of gravity is one of the most fascinating features of nature. And it sets the stage for something even more surprising. Our earlier calculations suggested that the ratio between electric and gravitational forces should remain constant no matter how close two electrons get to each other. But that conclusion relied entirely on classical physics. Once we begin examining nature at extremely small distances, another set of laws begins to take over. And those laws will radically change the story. So far, everything we have discussed has been based on classical physics. We treated the electrons as tiny particles separated by some distance r, and used Newton's law of gravity and Coulomb's law to calculate the forces between them. Within that picture, the results seem perfectly clear. The electric force dominates gravity by a factor of 10 to the power of 42, and that ratio does not change with distance. But the moment we begin pushing this thought experiment into extremely small distances, classical physics quietly stops being reliable. Nature begins to behave in a very different way, and the reason for that change is quantum mechanics. One of the most important lessons of quantum mechanics is that particles do not behave like tiny billiard balls with perfectly defined positions and velocities. Instead, they are described by probability waves. And those waves obey a fundamental rule known as the Heisenberg uncertainty principle. This principle states that the more precisely we try to confine a particle to a particular region of space, the less precisely we can know its momentum. In other words, if we force a particle into a very small box, the particle cannot simply sit quietly inside that box. Its momentum becomes uncertain, and that uncertainty shows up as a kind of unavoidable jittery motion. To understand what this means for our two electrons, imagine gradually squeezing them closer and closer together. Suppose we confine them within a region of size roughly r. According to the uncertainty principle, the uncertainty in their momentum must be at least on the order of Planck's constant divided by that distance. The smaller the region r becomes, the larger the uncertainty in momentum must be. This is not a limitation of measurement or experimental technique. It is a fundamental feature of how nature works. Momentum and energy are closely related quantities. If a particle acquires a larger spread in momentum, it must also acquire a larger spread in energy. We can estimate this energy by multiplying the momentum uncertainty by the speed of light. Doing this simple step allows us to convert the uncertainty relation into an estimate for the minimum energy associated with confining a particle to a region of size r. And the result is striking. As the distance r becomes smaller, the energy required to keep the particle confined grows larger and larger. At first, this might sound like a technical detail of quantum mechanics, but it actually has a very deep consequence. Einstein taught us that energy and mass are interchangeable through the famous relation E equals mc squared. That means if enough energy is packed into a small region of space, that energy behaves gravitationally just like mass. Energy can literally create particles. Now, let us apply that idea to our two-electron system. As we squeeze the electrons closer together, the uncertainty principle forces their energy to increase. Eventually, the energy associated with this confinement becomes comparable to the energy required to create an electron's mass. When that point is reached, the system has enough energy to produce additional particle mass. In other words, the vacuum itself can begin producing new particles. We can estimate the distance at which this happens by combining the uncertainty principle with Einstein's energy relation. When the numbers are inserted, the characteristic scale turns out to be roughly 10 to the minus 13 meters. To give some context, an atom typically has a size around 10 to the minus 10 meters, while an atomic nucleus is about 10 to the minus 15 meters across. So this critical distance lies between the scale of atoms and the scale of nuclei. What this calculation tells us is that once we begin probing distances smaller than about 10 to the minus 13 meters, the simple classical picture of two electrons interacting through static forces becomes incomplete. The energy required to confine the particles becomes so large that new physics begins to appear. Particle creation, quantum fluctuations, and relativistic effects all become important. The system is no longer just two particles interacting across empty space. Instead, it becomes a highly energetic region where matter and energy can transform into one another. This is the point where quantum mechanics and Einstein's theory of relativity begin to intertwine. The uncertainty principle drives the energy upward as we compress space, while relativity tells us that energy contributes to mass and therefore to gravity. That combination is going to change the story dramatically, because if the energy in the system continues to grow as we squeeze the electrons even closer together, then the gravitational influence of that energy will grow as well. And once gravity begins responding to that enormous concentration of energy, the balance between the forces we calculated earlier will start to shift in a very surprising direction. Once quantum mechanics enters the picture, our earlier comparison between the electric force and gravity begins to change in a subtle but very important way. In the classical calculation we performed earlier, the ratio between the electric and gravitational forces was fixed at about 10 to the power of 42. That result came directly from the masses and charges of the electrons and did not depend on the distance between them. According to that simple picture, no matter how close the electrons get, the electric repulsion should always dominate gravity by an enormous margin. But the moment we begin squeezing the electrons into a very tiny region of space, the uncertainty principle forces the energy of the system to increase. The smaller the distance r becomes, the larger the quantum mechanical energy associated with that confinement. And here's the crucial point. According to Einstein's relation between energy and mass, that extra energy behaves just like additional mass. In other words, the more energy we pack into the region between the electrons, the more gravitational mass the system effectively contains. This has a dramatic consequence. Gravity does not respond only to ordinary rest mass. It responds to energy itself. So as the uncertainty principle pushes the energy of the system higher and higher, the gravitational influence of that energy also becomes stronger and stronger. The electrons are still repelling each other electrically, but now the gravitational interaction is no longer determined only by the tiny rest mass of the electrons. It is being amplified by the enormous amount of energy required to confine them in such a small space. This means that our earlier ratio of 10 to the 42 is no longer fixed. As the electrons are squeezed closer together and the energy grows, the effective gravitational mass grows with it. Gravity begins to catch up. The electric force remains essentially the same because the electric charge of the electrons does not change. But gravity is now being strengthened by the rising energy density of the system. So we can ask a natural question. At what point does gravity become comparable to the electric force? In other words, how small must the separation between the electrons become before the gravitational attraction produced by this enormous energy concentration becomes roughly as strong as the electric repulsion between their charges? To answer this question, we can follow a simple chain of reasoning. We already know the expression for the ratio of electric force to gravitational force. If we set that ratio equal to 1, we are asking for the condition in which both forces have the same strength. Doing this allows us to solve for the amount of mass required for gravity to compete with the electric interaction. When this calculation is carried out, the result is surprising. The mass required is vastly larger than the ordinary mass of an electron. But remember, in our situation, the energy required to confine the electrons can act as additional mass. So we can translate this required mass into the equivalent energy using Einstein's equation. Then we use the uncertainty principle once again to determine the distance scale at which that much energy would appear. When we confine the particles, when the numbers are inserted, we find that the separation must be incredibly small, roughly on the order of 10 to the minus 34 meters. That distance is almost unimaginably tiny. For comparison, the size of an atomic nucleus is around 10 to the minus 15 meters. So we are now discussing a scale nearly 20 orders of magnitude smaller than the nucleus of an atom. At such a scale, the picture of physics changes completely. The energy density required to confine particles within such a minute region becomes enormous. Gravity, which normally appears absurdly weak when compared with electromagnetism, is no longer negligible. Instead, it becomes an essential part of the dynamics. The gravitational attraction generated by the energy of the system grows until it rivals the electric force itself. This is a remarkable shift in perspective. In our everyday experience, gravity is by far the weakest of the fundamental forces. But under extreme conditions, when energy is concentrated into extremely small volumes of space, gravity can grow dramatically stronger. The hierarchy between forces that seems so obvious at ordinary scales begins to collapse. And this realization leads us to an even more profound question. If gravity continues to grow stronger as we squeeze more and more energy into smaller and smaller regions of space, could this process continue indefinitely? Or is there some ultimate limit imposed by nature itself? To answer that question, we must now bring in one more piece of physics: Einstein's theory of general relativity, and with it one of the strangest objects in the universe, the black hole. At this stage, we have reached a rather strange situation. By squeezing the electrons closer and closer together, quantum mechanics forces the energy in the system to rise. Einstein tells us that this energy behaves like mass, and gravity responds directly to mass and energy. So the more tightly we try to confine the particles, the stronger the gravitational influence of the system becomes. This raises an obvious question. If the gravitational effect keeps increasing as we concentrate more and more energy into a smaller region of space, can this process continue forever? Or does nature eventually place a limit on how far we can push it? To understand how such a limit might appear, we need to take a short detour and think about how gravity behaves around massive objects. Imagine a small object sitting on the surface of a much larger mass, such as a planet. Because of gravity, the small object is attracted toward the larger one. If you want to remove the object and send it far away, you must supply energy to overcome that gravitational attraction. In practical terms, this means you have to throw the object upward with enough speed that gravity cannot pull it back. Physicists call this required speed, the escape velocity. It is the minimum speed an object must have in order to escape completely from the gravitational pull of a massive body. The formula for escape velocity depends on two things: the mass of the object creating the gravitational field and the radius from which the escape begins. The larger the mass, the stronger the gravitational pull, and the higher the escape velocity must be. Likewise, if the same mass is squeezed into a smaller radius, the gravitational field at the surface becomes stronger, which also increases the escape velocity. You can see this effect by comparing different planets. On Earth, the escape velocity is about 11 kilometers per second. On Jupiter, which is far more massive, the escape velocity is around 60 kilometers per second. But imagine continuing this process and squeezing more and more mass into a smaller and smaller radius. As the object becomes denser, the escape velocity keeps increasing. Eventually, something extraordinary can happen. If enough mass is packed into a sufficiently small region, the escape velocity can become equal to the speed of light. And since nothing can travel faster than light, not even light itself would be able to escape the gravitational pull of such an object. When that happens, the object becomes what we call a black hole. Light cannot escape from it, which is why it appears completely dark. The critical radius at which this occurs is known as the Schwarzschild radius. It tells us how small a region of space a certain amount of mass must occupy in order to form a black hole. If an object is compressed inside this radius, the gravitational field becomes so intense that an event horizon forms, and nothing from inside can send information to the outside universe. Now let us return to our two electrons. As we discussed earlier, when we squeeze the electrons closer together, the uncertainty principle forces more and more energy into the region between them. According to Einstein's relation, that energy behaves like additional mass. So effectively, we are increasing the gravitational mass inside the region we are probing. If we continue pushing the electrons closer together, the energy density eventually becomes so enormous that the mass equivalent of that energy would have a Schwarzschild radius comparable to the size of the region itself. When that happens, the region collapses into a black hole. This is the crucial point. The moment a black hole forms, no information from inside that region can escape to the outside world. Light cannot escape. Signals cannot escape. And no measurement we perform outside the black hole can reveal what is happening inside it. So if we attempt to probe distances smaller than this critical scale, by concentrating more and more energy into a tiny region, we inevitably create a black hole that hides the very information we are trying to uncover. In other words, the act of trying to observe smaller distances destroys our ability to observe them. Adding more energy does not help. In fact, it makes the situation worse, because more energy simply creates a larger black hole. Nature itself seems to enforce a fundamental limit. When the calculations are carried out, the distance at which this occurs is about 10 to the minus 35 meters. This tiny scale is known as the Planck length. It represents a boundary beyond which our current methods of probing space cease to make sense. It is the point where quantum mechanics, relativity, and gravity all collide, and where a completely new theory of quantum gravity is likely required to understand what truly happens. Up to this point, we arrived at the Planck length through a physical thought experiment. We imagined squeezing particles into an ever smaller region of space. Watched the energy rise because of the uncertainty principle. Converted that energy into gravitational mass using Einstein's relation, and eventually discovered that a black hole would form. That argument led us to a remarkable conclusion. At around 10 to the minus 35 meters, the attempt to probe smaller distances collapses the region into a black hole, preventing any further measurement. But there is another way to arrive at exactly the same scale. And this second path is in some ways even more elegant. Instead of starting with electrons and forces, we can look directly at the fundamental constants that appear in the basic laws of physics. When physicists think about the deepest theories describing nature, three pillars immediately come to mind. The first is quantum mechanics, which governs the microscopic world of atoms and particles. The second is Einstein's theory of relativity, which describes high speeds and the relationship between energy and mass. The third is gravity, which explains how mass and energy shape the structure of space and time. Each of these theories carries with it a fundamental constant that sets the scale of its effects. In quantum mechanics, the key constant is Planck's constant, usually written as h bar. This constant controls the size of quantum effects and appears in the uncertainty principle. In relativity, the central constant is the speed of light, c, which sets the ultimate limit for how fast information and energy can travel. And in gravity, we encounter Newton's gravitational constant, g, which determines the strength of gravitational interactions between masses. Now, here is an interesting question that physicists have asked for more than a century. If these three constants represent the foundations of quantum mechanics, relativity, and gravity, can we combine them to form natural units that reveal the fundamental scales of the universe? In particular, can we combine h bar, c, and g in such a way that the result has the units of length? To answer this question, we use a simple but powerful method known as dimensional analysis. The idea is to examine the basic units carried by each constant. For example, the speed of light has units of distance divided by time, meters per second. Planck's constant carries units related to energy multiplied by time, which ultimately reduces to kilograms times meters squared per second. Newton's gravitational constant has its own combination of mass, length, and time units that come from the law of gravitation. Once we express all three constants in terms of the basic units of mass, length, and time, we can try multiplying them together with different powers until the units simplify to just meters. In other words, we search for a combination of g, 8 bar, and c, whose dimensions correspond exactly to a length. Mathematically, we can imagine writing the desired length as g raised to some power. multiplied by h bar raised to another power, multiplied by c raised to a third power. Our task is simply to determine what those powers must be so that all the unwanted units cancel out. When we work through the algebra, something beautiful happens. There is exactly one combination that produces a pure unit of length. The result is the square root of g multiplied by h bar divided by c cubed. When we substitute the numerical values of these constants into the expression, the length that emerges is approximately 1.6 times 10 to the minus 35 meters. This number is precisely the same scale that appeared in our earlier black hole argument. That agreement is not an accident. It tells us that this length is deeply embedded in the structure of the fundamental laws themselves. Whenever quantum mechanics, relativity, and gravity all become important at the same time, this scale naturally appears. Using the same method, we can construct other natural quantities. For example, by combining the same constants in a slightly different way, we obtain the Planck mass, which is roughly 22 micrograms, surprisingly large compared with the masses of elementary particles. Another combination produces the Planck time, which is about 10 to the minus 44 seconds. That time represents the interval required for light to travel 1 Planck length. These Planck units are remarkable because they do not depend on any arbitrary human choices such as meters or kilograms. They arise purely from the constants built into the laws of nature. In that sense, they represent the universe's own system of measurement. And the fact that the Planck length appears both in our thought experiment with electrons and in this purely dimensional construction strongly suggests that something profound is happening at that scale, a place where the familiar descriptions of space, time, matter, and energy begin to merge into something we do not yet fully understand. Once the Planck length appears, it naturally leads us to another quantity that is just as fascinating, the Planck time. If the Planck length represents the smallest meaningful distance scale suggested by our current understanding of physics, then the Planck time represents the corresponding smallest meaningful interval of time. It can be constructed in a very simple way. Since the speed of light tells us how fast information travels through space, we can ask how long it would take light to cross a distance equal to 1 Planck length. When we divide the Planck length by the speed of light, we obtain a time of roughly 10 to the minus 44 seconds. This incredibly tiny interval is known as the Planck time. To appreciate how small that number really is, consider that 1 second already feels like a short moment in everyday life. Now imagine dividing that second not into thousands or millions of pieces, but into 10 to the power of 44 pieces. The Planck time is one of those pieces. It is such an unimaginably small duration that our current physical theories cannot meaningfully describe what happens at even shorter time. This idea becomes particularly important when we think about the origin of the universe. According to modern cosmology, the universe began in an extremely hot and dense state, often referred to as the Big Bang. As we trace the history of the universe backward in time using our current theories, we can describe the behavior of matter and radiation fairly accurately all the way back to a fraction of a second after the beginning. But if we continue pushing our equations further and further toward the very beginning, we eventually arrive at a point about 10 to the minus 44 seconds after the Big Bang. That moment is called the Planck epoch. During the Planck epoch, the conditions of the universe would have been so extreme that quantum mechanics, relativity, and gravity would all have been equally important. The densities and energies involved would have been vastly beyond anything we can reproduce in laboratories today. And here is where we encounter a fundamental limitation of our current knowledge. We do not yet possess a complete theory that consistently combines quantum mechanics with gravity. Without such a theory, our equations simply stop being reliable at these scales. This leads to an intriguing philosophical question about the nature of space and time themselves. One possibility is that space and time continue to exist smoothly even below the Planck scale, but that we simply lack the tools to measure them. In this view, the Planck length and Planck time represent limits of observation rather than limits of reality. Space and time would still be continuous, just hidden behind a boundary we cannot cross experimentally. Another possibility is far more radical. It may be that space and time, as we normally understand them, are not fundamental at all. Instead, they might emerge from some deeper structure of reality in the same way that a wooden table emerges from a collection of atoms. From a distance, the surface of the table appears smooth and continuous. But if you zoom in far enough, you eventually discover individual atoms and molecules. Some physicists suspect that space and time might behave in a similar way. At very large scales, they appear smooth and continuous. But at extremely tiny scales, their structure could be made of discrete building blocks, sometimes described metaphorically as atoms of space-time. However, developing such a picture is not easy. One of the challenges comes from Einstein's theory of relativity, which tells us that measurements of distance and time depend on the observer's frame of reference. If space were made of tiny discrete units with a fixed size, it becomes difficult to reconcile that idea with the symmetry principles of relativity. Because of this tension, researchers exploring these ideas must often rethink some of the assumptions underlying our current theories. The truth is that we do not yet know what really happens at the Planck scale. The mathematics of our current theories point strongly toward the need for a deeper framework, often referred to as quantum gravity. Several candidates exist, including approaches such as string theory and loop quantum gravity, but none has yet been confirmed experimentally. The Planck scale, therefore, stands as a frontier in modern physics, a boundary marking the edge of what our present understanding can describe. And that frontier carries a powerful message. It reminds us that even after centuries of scientific progress, there are still profound mysteries waiting to be uncovered. Somewhere beyond the Planck length and the Planck time lies a deeper description of reality that we have not yet discovered. Perhaps one day someone will find the key that unites quantum mechanics and gravity into a single coherent theory. And when that happens, our understanding of space, time, and the universe itself may change in ways we can scarcely imagine today.